let's see, we got x2, or xn plus 1. There's xn. So, make it more specific. Xn minus 3 cosine xn minus xn minus 1 over negative 3 sine xn minus, so I can do the same thing I did earlier. Yeah. So at least do that kind of level of, doesn't really matter. As long as you put it in the calculator correctly, you're fine. So now, anywhere you see xn, you put it the answer, memory key. So then we got, so to get us started, we need a guess. So I don't know who found which root.
Found one near pi halves, so it was point.
All right, so I'm thinking most of us probably found that one.
Yeah.
Right? So let's do that one. So pi over 2 is roughly 1.5. So I don't know, what did you use?
I just chose 1.
One.
Very vague.
Doesn't matter. So let's try 1, and then we'll try a different first guess and see what Newton's method does. Do. So if we try 1, so now we got xn plus 3 cosine. Answer. This is the most exciting part. Minus 1. 3 sine. What is that? Plus 1. Alright, so then I got 0.89.
Yeah, you just keep on. Yeah.
So I don't know, if not everybody started with 1, how many guys started with 1 as a first guess? How many guys waited until I started doing it up here?
I tried 3 as well.
What's up?
I tried 3 as well. I got a
Okay.
number, I think.
So you just say enter a few times.
I did it like 5 times. Just to
Do joy. So the minute you see the first 6 repeat, you can stop, right? Because it just said to correct out to 6 places. So 1, 2, 3, 4, 5, 6. So now it repeated out to there. It's even beyond that now. So I'm pretty sure it's this. Yes.
So for the root, how would you write that? Is there like a specific notation that you have to write, or is that just like the point, just a point like 0.889470?
Yeah. So be careful. It's not a point. It's just a value of x. I mean, if I said find the root of x minus 1, x plus 2, you'd say it's 1 and negative 2. So that's all we're doing. There's one root.
All right.
We're doing it in a very different way than we've ever done it. But we're still just finding roots, and it's just a list of x values that make the function 0. That's why you wouldn't even list them, because you know they're all 0.
Okay, yeah, I was just wondering how we would write it.
Oh, yeah. So let's try this whole thing again if I started with 2 instead of 1. But just hit second enter a few times to get my whole algorithm back. Thank God, because it took forever to type that in the first place. So if I hit enter, let's see what happens. All right, cool. So it's going to come right into it. And it gets there just about as quick, right? So at 2, which would have been in between these two, it's still good enough to get me there, right? But if I cross this, if I go up to like 3.5 and start there, let's see what happens.
What are we plugging in for xn?
So it's always the idea, we plug in something for x1, our first guess, and then the algorithm takes off. It takes that as a feed-in. We only have to take one guess. And we guessed 1, which is not a bad guess, because it's in between 0 and pi over 2.
So we,
Right, from the rough sketch I made.
so you did the f of x divided by the f prime of x, right?
That's what this is, yep. And of course, I took the minus from the algorithm and canceled over that. Yeah, cool.
Okay.
So what if I did, what did I just say, 3.5? See, let's see if it gets, now this is interesting. The minute I did that first one, now at 3.5, it's like right here, so that when it follows that tangent line, it went to 143. You guys see what's happening?
Yes.
So I went past this hump. So right at that 3.14, it's 0. If I put that in there, I'm going to go to infinity. But I went a little bit past that, so if I follow that tangent line, it actually goes out to 143. And then who knows what the hell, at 143, who knows what 3 cosine x minus 1 is doing, right? In fact, I'm not even looking at the right function. It's too bad for me, but it's the same kind of idea. But if I keep doing this, it's actually going to probably home in on the wrong, it's working its way back. It's bouncing on there. It eventually worked its way back. Freaking. I didn't know what it was going to do. Because if you're trying to find that root specifically, and your first guess is too far away, the slope to get your next guess might push you way far too, or it might push you over closer to one of these other roots. Are you guys semi with me? It all depends on what the hell's going on with the slope at the point you pick to start with. Because then you follow that slope to get your next guess. And depending on what the slope is there, it could take you way far away, or it could take you closer to some root that you don't want. I really desperately hope you guys kind of get this idea. That's why I said it was very sensitive to minor movements. It depends on what's happening with the function itself. Yes?
So how do we know which numbers to pick? Do we have to graph it first?
Exactly. That's this ugly thing here. It doesn't have to be pretty, but you do want to use a rough scale, and you do want to be roughly correct with everything. That's why I had to erase it, because I had a slope. I didn't do the +1. So then you get your idea about where these are, and then you kind of start guess of 1 is good. It's in between those two.
If the graph that it's asking us to plot is positively disgusting, just for this part, just to get our initial number, you don't care necessarily to use a calculator. I mean, like if it's just some really nasty graph, then it's going to end up going all over the place.
Our definition of nasty should be smaller than it was before this class, right?
It's definitely smaller, but I mean...
Yeah. You're not going to see something that... how do I say this? Do the sketch. I want to see that. Especially on a quiz or a test. I want to see some sketch. How influenced that sketch was by you looking at your calculator, that's up to you.
Okay.
Right? But I would love it if you guys just kind of...
Guessed.
Yeah, and just as an experiment on your ability just to get an approximate visual of the situation. You should be able to do that. It's a skill you should have. So don't push me too far, because I might make part of the test no calculator. So you want to be careful.
Part of the test.
Part of the test.
Conceivably, if we even if we picked a number that was farther away, though, conceivably if we picked a number that was farther away and we ran through the equation properly, it would just take us longer to get there, right?
Not necessarily. It might never get there. The periodicity of this, the fact that it keeps going through the same values, gives you a chance to work your way back. But if you had a function that forever went, then if you got in the wrong place, then you would keep getting further and further away, possibly.
Okay.
Right? So I thought maybe that would happen, but this one actually hit a point on the cosine part that took it back. And you can see that happening in the outputs. It was way at 143, 200, and then it was negative something, and then it bounced back to get the root. It all depends on if the slope ever lets you get back, or if the slopes just keep getting you further away.
Okay.
So Newton's method can very easily fail, but it's not necessarily... It doesn't fail always because of the method. It fails sometimes because our first guess sucks.
Okay.
So this just has to be a rough sketch, but the worse your rough sketch is, the worse your first guess might be. And you get some freaky things.
Okay.
Okay. So a good guess for that one would be...
I didn't think it was boring.
Yeah, I love it. So if we do, let me do a negative
I mean,
one.
it was really far off from like...
Oh, all right, let's try it. So start with -1. The beautiful thing about this is I don't care which root I'm going for, it's always the same algorithm because it's the same function. So I've already got the algorithm programmed in.
Does that mean we can do negative pi as well?
Of course, yeah. So it all depends on your initial guess, right? That's actually the way your calculator works. To find a root, if there are several roots, don't you have to put your cursor on it to say that's my guess? This is part of the reason why. It depends on your guess as to which root it's going to end up finding, right? So if my guess is -1, I should find this root. And eventually it homes in on it. There you go. Cool. And it was like negative pi over 2 is roughly negative 1.75 something. So that's not too bad. My sketch, lucky, I think, really is what I should say there. Because my sketch really did suck a lot.
I think I got the same answer as 3.
Yeah, it all depends on your first guess. A very small change in your first guess that you might realize that I'm probably going to do something like this to you on the test.
It might just hit that first.
You try 3 as an initial guess, and it goes to the root. You try 3.1 as an initial guess, and it goes to infinity. It could be very sensitive. It all depends on how quickly that slope changes. I really hope you guys understand that your guess looks at the slope of the function, and that's how it tells the next guess. Yeah. So whatever the hell your function is doing, if you move a little bit, you could totally go the other way. That's why Newton's method is simple, but sensitive to minor changes, because it's dependent fully on the slope, and your function could be doing weird things. Okay, that's all I have. Cool. So, the method's not too hard. Hopefully you guys I think everybody eventually got to the point where you're able to do this in the calculator. Sweet. That section's not too hard, and I love that section because I love the fact we base our calculators on a slightly adjusted formulation of something that was created centuries ago. It's just awesome. Okay. The last section should be very quick because we've already been doing this. Every test, I've given you a bonus section with a question like this. In fact, let me say it like this even. I can do it like that. Oh, let me do this. So I'm telling you the derivative of something is 3 secant squared x. So what could the function itself have been?
3 times x.
Yeah, so it's really, on one level, this is why they put section 4.9 in here. Because the next thing we're going to talk about really fully is antiderivatives. But one reason why you can put this section in the derivative section is if you understand them backwards and forwards, you freaking understand them, right? So if you understand how to do a derivative, but then you understand how to think backwards back, then you really understand derivatives. So I don't have any problem with them doing this now. Next chapter, we're going to really flesh out the full idea of antiderivatives and how they relate to something called integrals. Right? They are not necessarily equal to each other. We'll talk about that. So this would definitely have come from this. Now, is that necessarily the only answer?
No.
It could be, they did 3x.
Plus constant.
It couldn't be that. Because its derivative would add a 3x in there also, right? It's a good point.
Plus constant maybe.
Yes, good. So plus some constant. I can put any number I want to there, its derivative would still be this, right?
That's true.
And that only has to deal with, if I put tangent somewhere, do I really care if I move it up? Would that actually change the derivative? The slope is still the same. The function's moved up, but it's the slope at some point is still going to be the same. It doesn't matter. Are you guys with me? That's why it makes mathematical sense, why it's okay for this plus constant to be there. In fact, when we get to the full-fledged integration, which is really an extra form of anti-differentiation, that plus c is going to be a demon. If you forget it, I'm going to take points off, even though I used to forget it way back when. It's too bad. Yeah.
So whenever we take an antiderivative, we always tag on the plus c?
Yes, just to cover your ass. Or just to, because it could be something there that I don't know about. I don't have enough information. So what if I give you more information? So most of this section is just going to be, polynomials should be no problem. But actually, let me talk about polynomials real quick, and then I want to do something based on what you just said. What's the derivative of x to the n?
N x to the n minus 1.
So let's try to come up with the rule for going the other way. If I had x cubed, and that's f prime of x, what would f of x have to be?
X
1/4.
I love it. It would have to be a fourth power here, right? Because I'm undoing differentiation. Differentiation always takes the power down. So anti-differentiation should take the power up. So x to the fourth. So it seems like a general rule.
1/4 x to the 4th, right?
I know, it's not done yet, don't worry. A general rule for this should involve somehow x to the n plus 1, right? Going up instead of down. Okay, so far it makes sense, yes?
But if you're working the same way you would, wouldn't that be like 3x or 4x cubed?
Yes, I love it. So I'm not done here. I appreciate that. I'm not done yet. So this should be over 4. And it's exactly because of what you just said. So if I leave, I know it's got to be based on this because the power's got to be a fourth power because now I have a cube. So I know it's got to be a fourth power. Then I just think, what part of that derivative do I not want there? The stupid 4 that would come down. So I kill it. Right? Now, of course, what have I forgotten?
C.
Or not really, but I'm just waiting for you.
Plus C.
Good. So to complete this then, it should be over n plus 1. Whatever the hell that is, it's the same thing down there. Because what would this do if I took its derivative? Whatever it is, it would come down. Now there is one value of n that very obviously does not work for.
0.
0 is fine here.
-1.
There you go, that's the one. So you're like, it's going to be one of those two. If n is -1, then now we have an undefined thing here, right? So what it's saying is, if I have, this rule does not work if n equals -1, and what does that function look like? No. I mean, what's the original function look like? If n is -1, it would be x to the -1, right?
Whatever that is.
But we know what that guy's antiderivative. Where does 1 over x come from? Natural log. I love it. So it's got its own antiderivative rule. And I think I told this to you guys before. Natural log is the guy that actually bridges that gap. Because I can take a polynomial, and I can take its derivative. I can take its derivative. I can take its derivative. And then it's 0 forever, right? But then the rule keeps going for negative. So there's no bridge from positive to negative. Does that make sense? I can't start at positive power and somehow get to negative powers. So natural log is that bridge. It takes, if I take the derivative of natural log, I start off my negative powers and then let them go forever. You guys kind of with me? So the backwards rule should have that in there. There is no bridge. So if you're in -1 power, you're screwed for this. But the natural log is actually what saves you. If you're 1 over x, your antiderivative is natural log of x. And actually, it's this. I think we talked about that before too, right? X could be positive here, so it could be negative here. So you have to have an absolute value there. Now, what's missing in some of this stuff?
Plus C.
Good. Plus C. Plus C. I love it. Sweet. So part of this section, let it be easy. I know I had it as bonus questions, but most of you guys at least got most of the question right. You're able to think backwards, especially with polynomials. This rule here is pretty simple. And you didn't even really know the form of this. All you knew is you need a 4 there to kill the 4 that would come down. Yeah?
Shouldn't that just be f of x under the f of prime of x?
Oh, yeah. Thank you. So, in fact, I'm going to use some notation the book uses. The book says, given f of x equal to, what you got, Jen? I can't remember if we've seen this notation before, but big ass f, I don't think we've seen this before. Big ass f would be the antiderivative of middle f. Right? So it's sort of like the same, if I said f prime, I would put f here. But f to big F, that's the antiderivative. Are you guys with me? That's the opposite of differentiation. So if I have, this is going to maybe be interesting, but you can just apply the rule directly. If I have that, how do I get this? Follow the rule. -2 comes for the ride. What happens?
X plus 1.
X to the
1.
-1. It goes up, right? Opposite of differentiation. So this is going to suck. Once we start doing integration, we're going to have problems where you still have to differentiate too. So you got to change gears. And very often I can see the smoke coming. It gets really difficult sometimes to keep yourself on track. Which way you're going. It's really stupid easy to make a mistake. Differentiate when you're really trying to anti-differentiate. Oh God. Of course, what am I missing here? Over -1. What am I still missing? I like it. So then, collecting all this stuff together, is 2 over
X plus.
Good. And how can you check yourself? Check yourself. Take the derivative. I love it. That's supposed to be the antiderivative. To check it, you take the derivative. Make sure that it comes back out to this. Cool. Way cool. Now, here's the next level of this. And this will be the last thing for today. So if I have, I like it. So I've given you more information. So the new step here is that's new. And this is something we call in mathematics initial conditions. In physics we call it boundary problems. Something's happening at the boundary. This little thing is bouncing around the middle, and what happens at the boundary is going to help us figure it out. All that matters here is that's going to help me determine the value of, what is it that I don't know in general when I do an antiderivative? There's something I never know, the value of c. So if I know the value of the function at a point, I can help figure out what c is. So if little f is sine of 2x, this should be interesting. I love it. It's not that bad.
-2 cosine x.
You're not taking the derivative, right? So I like the negative part.
So it'll be negative.
Because where would sine come from? It would have come not from cosine, it would have come from negative cosine. And this is just a small taste of the gears grinding when you're thinking backwards. So if you put cosine 2x, it's not quite right. You need at least a negative. Now if you took this guy's derivative, what would happen?
You get 2 negative.
A 2 would pop out.
So you need a 2.
So you want to kill that 2 that's going to pop out over 2. Do you guys start to see what I'm saying? If you have a chain rule piece, and there's a constant going to come out because of it, you divide by that thing, it's going to kill it. If it's not here, it can't be coming out of here. So when you take the derivative, the 2 is going to come out, die right off the bat. So it's not there. And the derivative of cosine is negative sine, so that negative kills the negative, you would get there. You guys start to see. Now, of course, I left off. Good. Keep doing that on purpose. And then, now I can use that. I know f of pi over 4 equals negative cosine of twice pi over 4 over 2 plus c equals 3. And I made this nice. Should be.
C equals 3.
C equals 3. Because cosine of pi over 2 is 0. So c equals 3. So then the function is negative cosine 2x over 2 plus 3. Done. It's not always going to work that way. I just want to make this one nice. So it's just one extra step. You find the antiderivative like you normally would, and then you use that information once you have it. You plug it in, you figure out what c is. That just helps you pin. You know the shape of it from the derivative. You know the shape. You're just trying to pin where the hell this thing is with this information. That's going to pin it somewhere on your axis. Your axis. How we feel? It's not too evil. That actually should be one of the easier sections yet. It's my hope. Okay. And that's all I got for tonight. So, if everybody got a practice test, then you're golden. Please give me back my calculator thing. Oh, yeah. We do that right now.
That's you even nice break, huh?
You guys have a nice break.
Homework.
Yeah.